As an introduction to partial differential equations, we are going to present here one example of PDE, a partial differential equation, and it's going to be a quite simple to understand equation, I think, because it's based on a quite simple magnitude that is easy to understand. So the main aim will be to calculate the temperature of a one-dimensional bar. So we do have a one-dimensional bar here of length L, capital L, and we have that, let's suppose that the initial temperature of the bar is given by this expression here. So in general, the temperature of the bar will be depending on two independent variables, on x, and x is going to be the position of the point in the bar. So let's suppose this is the point. So if we consider we're taking the origin of the axis on the left border of the bar, that will be the x coordinate, which is fixed in the position in the bar, and also is going to depend on time, on t. So this function will depend on two independent variables, which is different from the case of the ordinary differential equations that we had some function. The y function will depend just on one independent variable. In this case will depend just on t. But here we have that the function will depend here, at least in this case, on two independent variables or more. For example, if instead of a one-dimensional bar we do have like a surface, then in this case the temperature will depend on two independent spatial coordinates, on x and y, and also on time. So, but here we're analyzing this simple case, and in this simple case we have that temperature will be depending on x and time. So besides this initial condition, we have said that in this case we have that it's given by this expression. So the temperature for as a function of x for t equals 0 is given by this expression, which in this case is 100 times cosine pi times x over 2L. So basically means that for x equal 0, I mean on the left border we have that this is 1, so we have 100, so the temperature here is 100. And the temperature here on the right for x equal L, we have this is cosine pi over 2, this is 0, therefore that's going to be 0. So that's the initial conditions. Besides these initial conditions, let's suppose that we are putting the left border of the bar in the oven, and the temperature of the oven is going to be 100, and we're not going to change the temperature of the border of the oven, so it will keep the temperature of the oven at 100. And as the left border of the bar is in contact, is inside the oven, that basically means that the temperature of the left border is going to be 100 for any time. That's why we do have this condition here, which says that the temperature for x equals 0 for any time is going to be 100. And then the other border, the right border, we're putting in, for example, let's say in contact with ice, which has a temperature of 0 degrees, and then we can say therefore, and as it will always have ice on the right border, then we can say that the temperature for x equal L, which is the right border, for any time will be 0. So these two conditions here, the conditions at the two boundaries, are called boundary conditions. So the constraints we do have now with the temperature of the bar are both the initial conditions and the boundary conditions. So remember that for the ordinary differential equations, we just had the initial conditions here. But in this case, as besides the temperature dependence here, we also have some dependence on any other independent variable, in this case, dependence on x. We have some extra conditions, which are the boundary conditions here. And with this constraint, of course, then the temperature of this bar, the temperature in the bar, is not going to be always the same. It is going to change with temperature. It's going to change with time. So the initial conditions will change at any other time. We'll have that the temperature in the bar will be different from the one we do have initially. And which is the equation governing that evolution with time? So in this case, we have that the evolution of the temperature is governing, it's given by the equation which is called the heat or diffusion equation, which is this equation here. So as you can see here, it's a partial differential equation. So you have these partial differential equations, we have partial derivatives here, both partial derivatives on time and partial derivatives on x, because remember that temperature depends here now on two independent variables. So the heat equation we do have here is the following. The partial derivative of the temperature with respect to time minus some constant. In the simplest case, this is just a constant, which is the heat or diffusion constant, or the heat conductivity, times the second order partial derivative of the temperature with respect to the position is equal to 0. And the principles of this equation in this case is based on some physical principles. But of course, other equations, other partial differential equations can have some principles in other in economics or in other subjects. But for the moment, we are not interested on analyzing on how can we derive these equations, because of course we are not interested in the physics of that equation. So basically we're going to take the equation, and the aim will be to analyze again here, for example, taking that equation, solving that equation, considering both initial and boundary conditions, in order to determine what's going to be the temperature of the bar for any x and any position and at any time. That will be the aim for that. And of course, the analytical calculations, the analytical solutions for that in general equations is going to be quite difficult, especially when we go farther from the simplest cases. And that's why we'll try to develop some numerical methods in order to deal with the resolutions of some partial differential equations.